No. We'll talk about that later. I think it's ability to achieve a wide range of goals environments. And things like dimensionality reduction are very important parts of being able to do that. But it doesn't necessarily capture the whole concept. Okay? That's my short answer.
The agent in the beginning.
But what about moral inferences?
Yeah.
For instance, is there a set of rules which create another dimension that say it can interpret and say this is an action I shouldn't take, or this is an action I should wait and do more often?
Right. There's no reason you couldn't put that in. At the moment, it's just try to play back. So there's no.
Put them in there.
That's just a reward, really, isn't it?
Yeah. So you can in theory try to put things in. Yeah. So maybe we'll talk about some of these later because we're actually going through an hour and a half so far. Okay. So I actually don't think this is going to really drive stuff forwards really soon. I think there's actually another area which is going to get some big mileage out of soon. That's my scary story for later. Okay, can we formalize this? I'll try to go through this reasonably quickly. Basically, when we've defined AIXI, we've actually defined all the parts that we need. We have all the machinery that we need to formalize what this is. Because we've defined an agent, we've defined succeed goals, we've defined a wide range of environments. We've got all the bits. And so if you just basically assemble all the pieces together from the AIXI machinery, it naturally comes together that you have a definition of intelligence. The only thing that's missing is that this says nothing about Occam's razor. And when we want to measure the sort of general ability to achieve goals in a wide range of environments, we need some way of weighting these environments. And essentially that's what Occam's razor tells us. It says that a priori simpler environments are more likely. And so if we want to test the agent in such a way that using Occam's razor makes sense, we need to weight the environments according to the complexity. And so if you put it all together, we know what our agents are, we've got our wide range of environments here, which are all our computable distributions. We've got our Occam's razor here, that's the complexity of the environment, or weighting. And then we've got the expected success of the agent in this environment. And we just consider all possible environments. So this is the wide range of environments. This here is the success. The goal is sort of implicit within the environment. And then we just take the whole lot. We just look at the expected performance across the whole space environment. So it contains everything. Is it intelligence? Well, I've just argued a second right before that this formalizes the definition I have. And so if you accept the informal definition I have, this is a formal characterization of it. Each of the symbols corresponds to part of the informal definition plus Occam's razor. So I think you can argue that in a formal and a very, very, very general sense, because that's what I want. I want a very general concept of intelligence here. It could apply to machines and anything super intelligent in the future or whatever. It formalizes a lot of these ideas about intelligence that we see from psychology and AI research and so on. It's very general. It says nothing about the internal workings of the agent. The agent can use magic to come up with its distribution over its actions. That's fine. We don't care. So we're not making any assumptions about what's going on inside. It doesn't have to be computable. In fact, AIXI isn't computable, and we can talk about the intelligence of AIXI. So it's very, very general there. Agents with high universal intelligence are very powerful. It turns out that, in a sense, this intelligence measure is the dual of AIXI. AIXI is the perfect agent. This is the measure that has the same structure where AIXI is the maximal element. Okay? And so we know, theoretically then, that if something has a very high universal intelligence, it's going to be optimal in this massive space of environments and so on. So having a very high universal intelligence theoretically really means something in terms of the power. Right? And it's also practically meaningful. If you had a system that was able to achieve a wide range of goals in a wide range of environments and converge to optimal and do all these things, then that's really quite a significant practical thing, right? So it's not meaningless in reality if you have a high measure. It's not anthropocentric. There's a big problem with the Turing test. You have to convince some judges that you're human, right? And so a key part of passing the Turing test is being human-like. You have to make spelling mistakes. You have to not be able to multiply two 20-digit numbers in under a second, right? You have to do all these sorts of things. So it's really a test of humanness. And the idea is that if you're sufficiently human-like, well, intelligence must have come along with it. But I would suspect that actually by the time you can pass a Turing test, you're already superhuman intelligence. Because you're able to fake being something of a completely different nature so convincingly that humans can't tell the difference. This says nothing about humanity. It's all defined in formal mathematics. It just comes from computation. And finally, it's formally defined. Even if you don't like my definition of intelligence, you don't agree with my equation, at least I've said exactly what I mean. There isn't any ambiguity in here. I'm not saying, oh, intelligence is the ability to have conscious interaction in a creative way or something like this, where I'm really just moving the problem of defining intelligence into all these other words that I haven't defined. I've actually given you an equation, and I've said precisely what all these parts are. So even if you disagree with me, you should disagree with me in a very specific way, because I've said exactly what I mean, okay? Yes?
So just on that point, how do you actually measure that intelligence though? So if you do have a machine with the AI, how do you assess that intelligence compared to a dot or a person?
Well, how do you practically apply the intelligence measure?
Yeah.
Okay, so it has this, again, we're working in theory, it's not a computable measure. Okay, so again, what we have to do is we have to approximate in practice. And I want to mention a few efforts to do that in a second. Oh, and finally, I would say that, okay, because the measure considers the space of all environments which are computable, have computable distributions. Right? It's in a massive, massive space. So if somebody comes up to me and says, your definition of intelligence, it's not the right definition because you haven't taken account of insert your favorite thing, consciousness, creativity, or whatever. Right? Okay, so let's take creativity. I would then answer, well, is creativity useful for being able to succeed in some environments? Now, there are some problems that require creativity to be able to, that helps you being creative. And if the answer is yes, then creativity is already being measured by this. Because you're using your creativity to be able to work better in these environments that require creativity in order to solve problems. So it's already taken care of it. What about consciousness? If consciousness is important, my question is, does it help you do stuff, consciousness? If it does, it's already being measured. If it's not being measured, it means that in no computable distribution over any possible universe can consciousness help you do anything, right? In which case, I don't really care. Well, in terms of intelligence, I don't care. Philosophically, I might care about consciousness or something, right? But it's not actually helping any system achieve anything. And that's what I'm worried about here. Okay, so can this be made practical? Less work has been done on this, but there are a few things going on. It's just sort of starting this area, I guess. I had some intention to do some things in this area, but I just haven't got around to it. I've been distracted. So Matt Mahoney has been essentially sampling from AIXI. What he does is he generates random Turing machines with some time bound on them and gets them to spit out a whole lot of stuff. And the stuff that comes out has essentially a kind of universal distribution. And then he uses it to benchmark compressors. And as you might expect, the really good compressors that work well in all the benchmarks work well against a universal distribution as well. This guy here, this was back in 2000, it was a while ago. He had some similar ideas about intelligence, and what he did is he put together a definition of intelligence using Commodore complexity, and then he approximated it using something called Legg complexity, which takes the time into account. So it's not just description length, it's time, like what you were asking about earlier. And then it's computable, and he then managed to come up with sequence. He only did sequences, he didn't do full interaction systems like I'm arguing for. So a bit more limited in that sense. And sure enough, he came up with sequences, and you had to then predict what's coming next. And unlike usually in an intelligence test, you get all these different sequences you have to predict, and some are harder than others. Where do they come from? Well, people think that this seems to